Hello, welcome to another module in this massive open online course. So, we are looking at Emery PSK modulation, and we have said that in Emery PSK constellation points are arranged inside on a circle, right, circle of radius a equals square root of Es. So, each symbol has an energy exactly equal to Es. So, the average energy is obviously Es, alright. The kth symbol is given as Sk equals, well, we have seen what the kth symbol is. The kth symbol is given as therefore square root of Es cosine 2 pi k over kth symbol is given as square root of Es cosine 2 pi k over m, and so this is your A1, this is your A2. And now what we want to see is the receiver processing. We want to see the receiver processing for Emery PSK. We have xt equals A1 P1t plus A2 P2t. Obviously, the received signal, again we have seen this several times before, we are considering an AWGN channel. So, this is xt plus nt, where nt is additive white Gaussian noise, okay. And well, therefore, I can write yt equals A1 P1t plus A2 P2t plus nt. And now I have to matched filter with similar to QPSK, QAM, etc. matched filter with both H1t equals P1 t minus t followed by sampling at t, and matched filter also with H2t equals P2 t minus t, okay. And we have seen before this match filtering operation, because P1 and P2 the pulses are orthogonal, this one will give us A1 plus EP plus N1 tilde, EP equals 1 energy of pulse. So, therefore, this is A1. I keep writing EP again just to account for the general scenario, and this thing is A2 plus N2 tilde, again note EP equals 1. This is energy of the pulse. N1 tilde, N2 tilde, these are Gaussian noise samples, mean equal to 0, variance equal to that is N naught divided by 2. And now you see there is a slight change in the detection scheme for Emery PSK in QPSK, for instance, and QAM. What we could do is we could look at R1t and R2t separately. That is, for instance, if we call this as R1t, R2t, we could look at R1t and R2t separately. That is, remember, Emery QAM can be thought of as comprising of two constituent square root Emery PAM constellations, correct. So, I can look at R1t as corresponding to one constellation Emery square root Emery PAM constellation along the x direction, x axis, the horizontal axis, and I can look at the other R2t as corresponding to the statistic for the square root Emery PAM along the y axis. Alright, so these are decoupled. Alright, so I can decide, I can choose or I can make decisions about A1 and A2 independently. However, that is not possible in Emery PSK, and that is what makes the decision scheme for Emery PSK slightly complex in comparison to, for instance, let us say a square constellation such as QPSK or QUAM. Okay. So, in Emery PSK what happens is, if you again remember, let me draw my picture. This is my circle, the points are arranged around a circle. For instance, you have this point which is square root of ES cosine 2 pi k by m. This is the kth point, this is square root of ES sine 2 pi k over m. Okay, and you have several such points. Okay, so these are the points of the constellation. And your decision statistic RT, for instance, let us say lies somewhere over here, that is RT, which is equal to now a combination of R1T and R2T. Okay. And now there is no other way except, remember, we can always rely on our minimum distance criterion. So, you have to measure the distances with respect to the various constellation. So, there is no other way other than measuring the distances with respect to the various constellation points and choose the one. So, what we have to do is look at the distance. So, the decision rule is to look at the distance to each, or to look at the distance to all the constellation points and choose one with minimum distance, and choose the one with minimum distance. That is the interesting aspect. So, basically I have to choose, so RT, so I have to choose point K SK, let us say this is again kth point of the Emery PSK constellation, then choose K such that RT minus SK, the distance, remember this is the norm, the 2 norm which can be used to represent the distance. So, we have to choose K such that minimize over K. So, choose K such that distance is minimum. Choose constellation point K choose the constellation point K such that distance is minimum, and I can express, remember, once again we have, remember, RT equals R1T comma R2T, it's a 2-dimensional point, SK equals square root ES cosine 2 pi k by m square root ES sin 2 pi k by m. So, the minimum distance, so the distance will correspond to will be, well, we know how to measure the distance between two dimensional points. So, this will be r1 t minus square root ES cosine 2 pi k over m whole square plus r2 t minus square root ES sine 2 pi k over m whole square whole under root. This is the distance between the output, okay, between output what we call test statistic, which is obtained after matched filtering and sampling, output test statistic RT and kth point of Emery PSK. And then what we have to do is we have to do nothing but basically choose the k which has the minimum, okay, and this is known as your, again, the minimum distance criterion or the nearest. Remember, we have already seen this in the context of, informally I had explained this informally in the context of well, PAM, QAM, etc. This is nothing but the nearest neighbor decoding rule, okay. This is nothing but the nearest neighbor decoding. So, that is the decision rule for Emery PSK. Okay, so that is the decision rule for Emery PSK, and that pretty much, now what we have to do is basically we have to look at the bit error rate for Emery PSK. Okay, we have to look at the bit error rate for Emery PSK. So, for Emery PSK, we have to look at the bit error rate for Emery PSK. Now, for this, to find the bit error rate, previously we had looked at, for instance, PAM, QAM, etc. We had an elegant way to look at the bit error rate. However, this, because of the nature of the decision rule, it is not very simple to find the bit error rate, but we have a way to get around this, alright. So, we will employ a different approach, which is basically based on finding the number of nearest neighbors. It's in fact an interesting approach, and in fact it can be used to tremendously simplify the bit rate computation for several other digital communication applications, right, where it's not very easy to compute the bit rate. Alright, so far we have seen scenarios such as PAM, QAM, etc., where it's relatively simple to compute the bit rate. Although elaborate, it's relatively simple. Alright, so here we are starting to see scenarios where it's not so simple to compute the bit rate. So I'll illustrate a general approach which can be used in such scenarios to compute the bit rate, and this is known as, basically it's known as the nearest neighbor decoding rule, or it's based on the number of nearest neighbors of each constellation point. Okay, so we will employ an indirect approach to calculate the bit error rate. Let me just highlight that. We will employ an indirect approach for the bit error rate. For instance, let us start with QPSK again. Let us go back to QPSK for a moment. Okay, to illustrate this, consider QPSK. Okay, in QPSK, if you remember, if I draw the constellation for QPSK, I have 4 points. Okay, square root of EB, square root of EB, square root of EB minus square root of EB minus square root of EB minus square root of EB, and finally minus square root of EB square root of EB. Now, if you look at any particular constellation point, for instance this, each constellation point has two nearest neighbors, so called nearest neighbors. Okay. So, each constellation point, observe that in QPSK each constellation point has two nearest neighbors. Let us denote the number of nearest neighbors by alpha. So, alpha equals 2, 2 nearest neighbors, alpha equals 2. Okay. Now, further the distance to the nearest neighbors is, well, if you look at the distance between these 2 points, it is twice square root of EB. And we can formulate the bit error rate, approximate expression, symbol error rate, not the bit error rate, rather in fact symbol error rate is often abbreviated as SER, just as bit error rate is abbreviated as BER. This is equal to, and this is an interesting expression, alpha, which is number of nearest neighbors, times Q into d min, distance to the nearest neighbor, divided by square root of twice N0. Okay. So, this is an interesting expression for the bit error rate, and it is very helpful in such scenarios where it is difficult to compute the exact bit error rate. Okay. So, alpha equals number of nearest neighbors, as we already said, number of nearest neighbors, d min, that is equal to distance to nearest neighbor, and this is a very useful expression. Let me note that also, it is a very useful expression to compute the error rate of a digital communication system or a digital modulation scheme. Error rate of digital communication when exact expression is difficult to obtain. Okay. When exact expression is difficult to obtain. Now, let us go out to our Emery PSK. Okay. So, now let us go to our Emery PSK constellation, and here we want to find again the symbol error rate using the nearest neighbor criterion, okay, using this approximation based on the number of nearest neighbors. Okay. And again, if you go to your Emery PSK, I draw the circle, let me just draw it a little bit better and a little bit so as to illustrate it. Now, if you look at this, okay, now if you look at this, for instance, let us look at any constellation point, or let us look at any constellation point. We can look at any constellation point, for instance, corresponding to k equal to 0. Remember, phase is 0. Now, each constellation point has two neighbors. Okay. So, each constellation point has two closest neighbor. Each constellation point has two closest neighbors, and now remember, this is equal to square root of ES, this is equal to square root of ES. If I look at the distance, correct, let us now look at the distance d min. Now, if I draw a line from the center to the line joining these two constellation points, it is perpendicular, okay. And this angle, remember the total angle, the total difference, the total phase difference between 2 points is 2 pi by m. So, this angle is 2 pi by m, which means this angle is pi by m, okay. So, this angle is pi by m, therefore, this half of the distance. So, d min by 2, and you can check this, d min by 2, or let me just write this over here, d min by 2, you can verify this is equal to square root of Es into sine pi by m. That is an important result. So, this is square root of Es into sine pi by m, and this basically is your d min by 2, and therefore implies d min equals twice square root of Es into sine pi by m. That is the whole point, okay. So, d min for Emery PSK, and you can check this, equals square root Es or 2 square root Es sine pi by m, okay. I hope that brief derivation, it is rather simple, it is based on your high school geometry, principles of high school geometry. It is based on principles of high school geometry, that is, if you look at a chord, right, on the circle, and if you draw a line from the center to that chord, the line from the center is perpendicular to the chord, that is one, and we have used the fact that the radius of the circle is square root of Es, and the phase difference between the points is 2 pi over m. Therefore, if you look at this chord, line joining the center to the chord, it bisects that angle, right. So, the angle is now pi by m, okay, and you can use these simple principles and derive it, but it might just take a little bit of looking at it carefully, okay. And therefore, now it becomes really simple, I do not have to go through an elaborate derivation. In fact, thanks to the result that we have probability of error is 2, well, number of nearest neighbors alpha equal to 2, that is the first thing, let us note that also, I think that is also equally important. So, number of nearest neighbors alpha equals 2, let us note that. So, we have probability of error equals twice q, well, d min is twice square root Es sine pi over m divided by 2 n naught, which is equal to twice q square root of twice Es sine square pi over m divided by n naught, okay. That is the expression for the approximate probability. Remember, this is not an exact expression, this is an approximation, and in fact this approximation is very close. So, in fact, this is an approximation, let me just again emphasize that this is an approximation, but this approximation is very close as Es by n naught increases at highest. So, this is an approximation rather very useful. It is an approximation for symbol error rate of Emery PSK, and the approximation is very tight at high ES over N naught. Or we can say, instead of tight, let me use a simpler word, the approximation is very close to actual SCR at high ES over N naught. Okay. So, that is pretty much what we have for Emery PSK. Alright. So, we have seen Emery PSK, we have seen the receiver design for Emery PSK. In the previous module, we have seen the constellation, the waveform for Emery PSK, alright, how to compute the average symbol energy, and now we have seen in this module, we have seen the receiver design, the match filtering operation, correct, and the optimal decision rule, which is based on, it's nothing but based on the nearest neighbor decision rule, and we have also seen an interesting framework, although we have interesting framework to compute the approximate probability of symbol error for any general constellation. And although I have illustrated in the context of QPSK and Emery PSK, this is a very general, the nearest neighbor criterion based approximation that we have seen to compute the symbol error rate is very general and can be used in a wide variety of scenarios. So, using that we have computed the symbol error rate of this Emery PSK constellation. Alright. So, we will stop here and continue with other aspects in the subsequent modules. Thank you very much.